All right, we're going to take a look at some additional successive approximation problems. These will be in your, or these are in your notes, so you can sort of follow along, write down what I'm doing. We're going to look first at example 8.6, which says how many moles of copper 2 hydroxide can be dissolved in 1 liter if the pH is 7.8, and they give us the KSP. All right, so obviously the first thing we do is we write our equilibrium expression. So we've got that done, but we also recognize that if the pH is 7.8, we're going to have to take into account the hydroxide concentration that is already there in the solution. So we can do that. We know that OH minus is just going to be 10 raised to the negative of 14 minus 7.8, and we get 6.3 times 10 to the minus 7. So that's already in the solution, the 1 liter, before we even add copper hydroxide. All right, so we write our KSP equation. We say 5.6 times 10 to the minus 20th is equal to x times 2x plus the hydroxide concentration already there, 6.3 times 10 to the minus 7th, squared. We put the squared because of the coefficient 2 in front of the OH minus. All right, now we hope that we can make a simplifying assumption, because if we don't, we're going to have x cubed terms, because the 2x in the parentheses squared would give us 4x squared, multiplied by the x would get a 4x cubed term. And we don't really know how to solve cubics. So let's see if we can simplify this by making an assumption. Our assumption, as always, significant figures rules the day. So we say that 2x is less than 0.05 times 10 to the minus 7th, because we're trying to ignore the 2x compared to the 6.3. So that would mean that x would be less than 2.5 times 10 to the minus 9th, all right? Now, if we do that, we can cross out the 2x, and we just get 5.6 times 10 to the minus 20th is x times 6.3 times 10 to the minus 7th squared. We can easily solve for x. But the problem is that x is 1.4 times 10 to the minus 7th. Okay, so I'm off by a factor of a couple hundred. Okay, I'm not really that close. So our assumption is not valid. Okay, but let's use that. Let's use this as a starting point. Let's see what happens. Okay, here I've rewritten my equation at the top of the page, so I've got room to work. All right, we're going to assume that x is 1.4 times 10 to the minus 7th, even though we know it's not. We're going to use it, and we're going to plug it into the equation where 2x plus 6.3 times 10 to the minus 7th squared, and we're going to solve for the other x, which is outside the parentheses. So when we do that rearrangement, we get that x is 5.6 times 10 to the minus 20th divided by that rather large term at the right. And so I plugged in 1.4 times 10 to the minus 7th in red. When I do all that math, I get 6.76 times 10 to the minus 8th, or 0.676 times 10 to the minus 7th. So originally I had 1.4 times 10 to the minus 7th. Now I get 0.676 times 10 to the minus 7th. Okay, our answer is closer, but not quite the same as the first time. But now I take this second value of x, I solve this problem again. Okay, now I've rewritten it. We try to solve for the value of x, 5.6 times 10 to the minus 20th, our KSP, divided by our new quotient, our new value of x that we're going to use. And now when I solve it, I get 0.956 times 10 to the minus 7th. Okay, now you'll notice, if you do notice, that 0.956 is between our first answer, which was 1.4, and our second answer, which was 0.676. So we see that, hey, I seem to be in between these two. And if I just keep doing this, and I keep track of our solutions, I see what happens. I'm rounding rather than using all my sig figs. I'm just rounding. Okay, now if I do this 8 times, I get an answer that converges to or stops changing at a value of 0.87 times 10 to the minus 7th. Okay, so that's going to be our answer, 0.87 times 10 to the minus 7th. All right, let's take a look at another problem. Here's example 8.8. Now, we haven't got to organic chemistry. We'll do this. These particular things will be chapter 13, which will be pretty close to the end of the school year. Don't worry about what these are called. We'll deal with that in the course of the year. But this is acetic acid plus acetone reacts to form an ester plus water. Okay. Now this reaction has a KEQ of 4. Well, 4 is greater than 1. Okay. Now if I take 200 milliliters of 12.3 molar acetic acid and 100 milliliters of 11.2 molar acetone, I react this, the whole thing's diluted to 1 liter. What do I get when I finish? What's my equilibrium concentrations? Okay, this looks really hard, but it's not. We can easily calculate the starting concentrations, right? I take my concentration times my volume to get the number of moles. I divide it by 1 liter, which is pretty darn easy. I get 2.46 molar acetic acid, or I'm abbreviating this as HAC. So at equilibrium, my concentration is going to be 2.46 minus X. I can do the same thing with my, sorry, this is ethanol, not acetone, it's ethanol. I can take my volume, 0.1 liter, multiplied by molarity, divide the whole thing by a liter to see how much I've got. I've got 1.12 moles, or molar, ETOH, ethanol. And my equilibrium concentration, therefore, is going to be 1.12 minus X. Can I write an equilibrium expression? Sure, we know how to do that. So my initial concentrations, you can see my numbers are lining up with the reaction at the top of the page. Initial 2.46, 1.12, 0, and 0. My change, minus X on the left and plus X for the things on the right. Okay, here, these are not solids dissolved in water. Water is a product of this reaction. So this is a case where I actually have to include it. I didn't have water on the left. I do have water on the right. So I need to include this in my calculations. So my equilibrium concentrations are going to be X and X on the right, 2.46 minus X and 1.12 minus X on the left. Okay? So I'm just rewriting it to get it to the top of the page. So I write my expression. KQ is 4 times X squared divided by the product of these two first order quantities. But here's the issue, and this is why we're doing this problem. K is no longer smaller than 1. K is larger than 1. And so we can't really assume X is small because it's not, right? X is actually fairly large because that's how we get a K. That's 4, right? So X is not insignificant. But that's okay. These are all first order terms, so all I'm going to be left with is a quadratic. I know how to solve a quadratic. If I write this all out and get myself a quadratic, I got to do a few steps, but it's not hard, right? It's 10th grade algebra 2, and I can get an equation that becomes 3x squared minus 14.3x plus 11, and I've gotten rid of like 5 significant figures and got myself down to 3 significant figures. And I can solve that with the quadratic formula. I get 2 values of x, which I expect for a quadratic. But here's the interesting part. X cannot be 3.8. It's a it's a algebraic solution to the problem, but it's not a physical solution to the problem. Because if x was 3.8, then I go back to the top, I would have negative quantities for both acetic acid and ethanol. Can't have negative quantities. What does that even mean to have a negative quantity? So I have to pick the other value of x, which is 0.964. And when I do, well, those give me positive quantities. So for acetic acid, 2.46 minus 0.964 is 1.5 molar. And then for ethanol, 1.12 minus 0.964 gives me 0.156 molar. And we're finished with this problem. Okay, looks hard. The hardest part is translating the English into chemistry. Once we get to the chemistry, it's not difficult. Okay, we're going to take a look at one more here. Okay, so here I've got, this is called the Haber-Bourne process, where I take nitrogen and react it with hydrogen to form ammonia. This is what the Germans used in World War I to make their own ammonia, which could then be used as both fertilizer, but really as a starting point to make explosives. So this is what kept Germany in the war in World War I. Otherwise, they would have been defeated long before they were. All right, the Kp, P, that's a pressure equilibrium because these are all gases. Kp is 0.00412. We're not real high. But the question is asking, what are the equilibrium pressures of all the gases? Okay. As always, I start with stoichiometry, write a reaction. Okay. The nitrogen to hydrogen ratio is 1:3. And therefore, I'm going to need 3 times 1.10. I guess what I didn't put here was my starting pressures. For nitrogen, it was 1.1, and for hydrogen, it was 4.1. Those were my starting pressures, okay? So equilibrium for nitrogen is going to be 1.1 minus x, and for hydrogen, 4.13 minus 3x because of our stoichiometry, and for ammonia, my equilibrium pressure is 2x. Okay, yeah, I should have written that in first, and I didn't. All right, so now I can write a K. It's built on pressure instead of concentration, but that's okay. So Kp is 0.412, and that's equal to 2x quantity squared divided by the product of my left side reagents. I make an assumption that x is smaller than 0.005 or that 3x is smaller than 0.005. The more limiting case is the one on the right, the second one. So x is 0.00167, but when I solve for x, I get 0.279, not valid. So I can do these successive approximation terms, or approximation method, and I can do this 8 times, and when I do, I get the same thing as in the previous problem. X finally gets to an unchanging answer of 0.199. You could probably round that to 0.20. And that gives us our equilibrium concentrations. All right, we're going to stop here. I've got one more video for the remainder of these problems.